In this video, we're going to discuss directional derivatives and the gradient. So we've already seen previously that the partial derivative with respect to x gives us the slope of the tangent line in the x direction, and the partial derivative with respect to y gives us the slope of the tangent line in the y direction. Suppose you want to determine the slope in some other direction. So first, let's look back at the diagram for a tangent plane to try to visualize what we actually mean by the directional derivative. Okay, so let's look back at the section on tangent planes, and specifically these three diagrams here. Right, so if you look at these graphs, the way the grid lines are drawn onto the graph, that essentially represents the x directions and the y directions, right? So like in this example here, this is representing the y direction, and then these following along these grid lines would be parallel to the y direction. And similarly here, these grid lines would be parallel to the x direction. These grid lines would be parallel to the y direction. So the pink arrow here is indicating the direction of the slope that for the partial derivative with respect to x, and similarly here the partial derivative with respect to y is the slope indicated here. So suppose now again we're on, say, some specific point for the tangent plane, and we want to travel in a different direction, right? So again, the grid lines shown on the tangent plane here indicate directions that are parallel to the x or y axis. So for example, in this diagram, the traveling in this direction would probably be parallel to the x-axis, and then traveling in this direction would be parallel to the y-axis. So suppose we want to travel in some other direction in between, like like here in some diagonal direction, not following the grid lines. So there's a slope in this direction also, that's in between the slope in the x direction and the slope in the y direction. So that's what we're trying to calculate when we calculate a directional derivative, right? So a slope in some direction, say traveling along the tangent plane like this. So the good thing is that once you have the partial derivative with respect to x and the partial derivative with respect to y, just some combination of them will give us the directional derivative that we want. So so the formal definition is given here, where first you pick a specific point on your graph and the direction that you want to calculate the slope in. So the direction vector here should be a unit vector, meaning that u has length 1, right? So the unit vector means that the magnitude of u is equal to 1. So this is important because sometimes in an example they might give you a direction vector where the magnitude is not equal to 1, and so you have to first normalize the vector before doing any calculations. In any case, once you have your unit vector direction, then essentially the calculation of the directional derivative is just a dot product with the direction vector, and so this notation here is called the gradient vector, and the gradient vector is just the vector with the two partial derivatives as the components. So we give it a special name, the gradient, because it's also useful in other contexts. So again, the calculation of the directional derivative is fairly straightforward. once you have your unit vector direction, then it's just the calculation is just a dot product. So another thing to be aware of with this calculation here is that if, say, the unit vector is the vector 1, 0, right? So this is the vector that only points in the x direction. Then just plugging it into here, right? So this would be a 1, this would be a 0, and then the calculation is exactly the partial derivative with respect to x. And if the unit vector is the vector 0, 1, then you get exactly the partial with respect to y. So the directional derivative is a sort of a generalization of just the partial with respect to x or the partial with respect to y, so that it can point in the slope can point in any direction. Okay, so with that in mind, let's use this formula to calculate an example. So in example 1 here, we're given this function f of xy, and we're asked to calculate the directional derivative at the point 2, 1, and in this direction v. So in the notation of the formula above here, the point is located at a, b, right? So in this example, my a is going to be 2, and my b is going to be 1. And as I mentioned before, to actually proceed with the calculation, you want your direction vector to have magnitude 1. But if you look at this given direction vector, this vector does not have length 1, right? So the magnitude of v, let's just calculate it real quick, is the square root of 2 squared plus negative 1 squared. So that's just 4 plus 1. So this is the square root of 5. So we have to first normalize the vector, right? So we want the unit vector to be, so to normalize, you just divide a vector by its own magnitude, right? So just dividing both these components by square root of 5, I get 2 over square root of 5, comma, negative 1 over square root of 5. Okay, so now I have my unit vector direction. And so what else do I need? So to calculate this, I need my two partial derivatives. Right, so let's use the gradient notation. Right, so gradient of f is the vector with the partial derivatives. So what is the partial with respect to x? So taking the derivative here, y is a constant, so you get 2xy. And this only contains y, so the partial with respect to x, this term goes away. And then now the partial with respect to y, so now this is constant, so it's just a constant times y, so you get x squared. And then here we just differentiate with respect to y, so that's minus 12y. Okay, so I have my gradient vector, and so so in the calculation here, I need to calculate the gradient at the specific point, so the point 2, 1 in this case. So let's calculate that. So gradient of f, where x is 2, y is 1. So what do I get? So 2 times 2 times 1, comma, and 2 squared minus 12 times 1. So the gradient of f at the point 2, 1 is the vector 4, comma, and what is this? 4 minus 12 is negative 8. Okay, so so now I just need to put it together. So the directional derivative is the gradient at the point A comma B, dot product with my vector u. So writing it out, it's 4 comma negative 8 dot product with 2 over square root of 5 comma minus 1 over square root of 5. So dot product just means that I multiply the corresponding components, so 4 times 2 gives me 8 over square root of 5. Then I have minus 8, and then times negative 1 over square root of 5. And then negative times negative gives me a plus, and then 8 plus 8 is 16 over square root of 5. Okay, so that's the value of the directional derivative in this direction at this point.